Hey, this is Math 6, Unit 1, Lesson 3, Reasoning to Find Area. So we're going to be decomposing, breaking apart, and rearranging shapes today to find their area. So a little bit of an extension from what we did the day before. Alright, so first one. Is the area of figure A greater than, less than, or equal to the area of the shaded region, notice this shaded part again, in figure B, and be prepared to explain your reasoning. So the question is, if I measured up all that blue, does this blue, is it the same, less, or equal to this blue here? And what's your reasoning there? Now to figure this out, what you might want to do is figure out, well, what about this little piece there? What is that little extra little thing right there? If you took some patty paper, and I don't have any patty paper today, so I actually got some stamps out of the drawer at my house and used the back side of that. I think this will work here. Let's see. Yep, that'll work. And if I trace that little extra bit right there, that will allow me to move this little bit and see what happens when I move this. When I move this here, I can slide it, and what do you notice? It fits nice and snug right on top of that gap space right there. So I actually would be able to fill that gap with that piece that's hanging out in the edge. And if that's the case, then the next question would be, are these the same exact size? Well, let's find out. If I take this gap here, well, that's nice, it's right there on the edge of the paper. Didn't mean to quite do that, but there it is. And I can take a square, and I just trace that square all the way around. I know it goes all the way to the edge there. And then we see, does that measure line up there? And sure enough, they're the exact same size. So in this case here, we would say that figure A is equal to the area of the shaded region of figure B. This little piece fits right inside of there, and so when you put them together and make them overlap, we end up with the same exact area. Alright, part 2. Each grid, move this a little bit, there we go. Each grid square is one square unit. Find the area in square units of each shaded region without counting every square. So our goal here is not count every square. We know that you could go 1, 2, 3, yes, that's great, but our goal is to not count every square. Our goal today, if you remember back at our objective, is to learn how to decompose and rearrange shapes. That's our goal there, decompose and rearrange them. So, on this first one, what you might do, and this is what I think I would do first, I would continue this line right there to decompose, which means I'm going to break that apart into two rectangles. These are two rectangles that I'd probably have an easier time kind of measuring with lengths and widths. I can notice that it has 6 across and 2 down, so I have a 2 times 6, which gives me an area here of 12. And here I have a 3 by 4, so an area here also of 12. And when I combine those together, I would say there's an area here of 24 square units. Not counting everything else up, but just looking at two different rectangles there. Okay, on this next one, okay, a couple things I might do. I could say that the gap is a 3 by 3, so this gap has 9 units inside of there. The whole square is a 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. To 6 by 6 square. So the whole blue area is a 36 units, but I am not including the 9 on the inside, so I'm going to take those away, and I'm left with just 25. So 25 square units there. So those ones, not too bad. You know, again, you probably could go, well, I could count them and figure that out. But when we get to C and D, we notice that it's just not quite the same, is it? Okay? We're going to have to break some things here and also not just decompose them, but work on the rearranging of them. So let's take a look. First of all, I notice that this triangle has 1, 2, 3, 4 and a length of 2. This one also is a 2 and a 1, 2, 3, 4. Here's a 2 and a 1, 2, 3, 4, 2, 1, 2, 3, 4. So all these triangles have the same exact measurements, which means this. If I was to take this triangle right there, this is where patty paper can kind of help you a little bit. If I was to take this triangle and measure that right there. What happens if I rotate that around a little bit? I don't know if you can see this very well, since it's not the best patty paper. I think you can. Notice that I can draw that same triangle right on top of it, right beside that one, or right above it. So I'm going to do that here. I'm going to draw it out. 1, 2, 3, 4, and there. So basically, if I was to swing this one down to there, I would have another rectangle, wouldn't I? Got that idea? And if I was to swing this one up to there, I could have a rectangle right here, right there. Now with that rectangle, because it's a 4 by 2, I know that that has a whole value, the whole thing, when I swing it up there, of 8. And that has the same one, 4 by 2 of 8, and 8 plus 8 is 16. So I'd have 16 square units for that one right there. Alright, kind of cool. It'd be hard to do it another way. I mean, I could count the squares, 1, 2, 3, 4, 5, 6, 7, 8, but I have all these partial ones. Hard to figure out what those are. But because that can be decomposed and then swung up there and rearranged to make a rectangle, I'm in good shape. Now when you look at D, one of the things you might notice is, it looks a little familiar to C, the C problem, but it's like the inside part, isn't it? Right? So there's a couple ways of thinking about this one. I could decompose this and break it up. That's one way of doing it. So let's do that first. If I decompose it, I'm looking to make a right angle triangle. That means I draw a line here and here, and I make a right angle triangle right there. I can make another one by going right here and here. I can make another one by going down to here and here, and another one by going here to here. So now what I've created are 1, 2, 3, 4 triangles and a square on the inside. This square has a 2 by 2, so it has a value of 4. And this part here, again, I have a 4 by 2 triangle. So let's flip this guy all the way over to there and make him a 4 by 2 like this. Is that okay? And then let's flip this guy all the way over here and make a 4 by 2 right there. So now I have a 4 by 2, which is 8. I have a 4 by 2 here, which is 8, and I have the 4 in the middle, which is 4. So 8 plus 8 is 16, plus 4 is 20. So I have an area of 20. That's one way of solving this problem there. The other way I could solve it, if I wanted to, would be to look back over here and recognize that what I'm dealing with is this space. I knew that the blue that's shown there is 16, and that white space is the same as this blue space here. Well, this has a length of 1, 2, 3, 4, 5, 6 by 6. So the square that goes around there is actually 36 units. Follow me? This whole square is 36. Well, what's missing is the inside piece. If the outside was 16, and I take the outside away, what's left is what's in the middle, which is going to be 20. So there actually were a couple ways of approaching that problem there. That's kind of good. Again, you might see some things one way and some things another. Just kind of makes math fun. Different ways of approaching it. All right. All right. Rearrange the triangles from C so that they fit inside figure D, and color a draw and color a diagram of your work. Okay. So, which we kind of did here actually. We have the same ones. If you look at ours, what we did, we have a 2 by 4, which is 2 by 4, and that is exactly what we did. So I could draw it over here again for you. We just happen to do it that way. All right, so a 2 by 4 is 1, 2, 3, 4, and we go out to 2. Oops, like so. All right, and then 1, 2, 1, 2, 3, 4, and then we go out like so, and 1, 2, 1, 2, 3, 4, out like so, and then 1, 2, 3, 4, and 2, and there we go. So that's what we have. So there's our square in the middle with our 2 by 4 type of triangles. All right, third activity, off the grid. Find the area of the shaded regions in each figure and explain and show your reasoning. So we're going to do some decomposing and rearranging to make this work. All right, so first thing we want to do, this is a 3 and a 5. This is a 3 as well, sharing that 5 side. So if we take this triangle and we move it up to here, we would end up with what? We'd end up with a rectangle that's a 3 by 5, like so. And 3 times 5 is equal to 15 centimeters squared. All right, over here, we've done this one just a second ago, right? We can slide this piece down to here to make a rectangle right there. That rectangle becomes a 2 by 4, and 2 by 4 is equal to 8. And we can slide this one up to here if we chose to go there. And again, this one's also 2 times 4, which is 8. So 8 plus 8 is equal to 16 centimeters squared. And the last one here, we have a large square, which is 5 by 5, which is 5 times 5 is 25 centimeters squared. But then we have something on the inside we need to take out, don't we? This is a 2 by 2, so 2 times 2 is 4. So we're going to subtract the 4 centimeters squared on the inside to leave us with 21 centimeters squared for choice C. So a couple of things we're doing, right? This one is just a rearrange, right? So we're just rearranging it, really decomposing it because we're cutting it in half, I guess. So decompose, rearrange. This one here, we're decomposing by chopping them there and rearranging it here. This one, we're not so much decomposing and rearranging as recognizing that we can take something out of something else, okay? There's another little just trick there. So let's take a look at our summary for today's lesson. It says, there are different strategies we can use to find the area of a region. We can decompose it into shapes whose areas you know how to calculate, find the area of each of those shapes, and then add the areas, right? So if we have something like this, we break it apart into 2 rectangles and add them up. We can also decompose it and rearrange the pieces into shapes whose areas you know how to calculate, right? We can calculate the area of a rectangle or square. So if we take these triangle pieces and we cut them apart there, slide it over, we end up with a rectangle, and we can figure that out. We can also consider as a shape of the missing piece. Calculate the area of the shape and the missing piece, then subtract the area from the piece from the area of the shape, which is what we did in the previous problem. So we figure out what we know and figure out, well, what are we missing, and let's subtract that. The area of a figure is always measured in square units. When both side lengths of a rectangle are given in centimeters, then the area is given in square centimeters. So this is 8 times 4 is 32, but it's in centimeters, we'd say square centimeters. And that short abbreviation for it, right, I did it in one of my problems here, we would write as centimeters squared. So you might see that from time to time as well. So it looks backwards, we don't write just square centimeters. You could write down square centimeters, but traditionally you're going to end up writing it this way, just to kind of see that. So if you notice that, if your teachers write it that way, that's just kind of a thing we've always done in math, so probably it's the way they're writing it down the board. That's okay. It means the same things. It means centimeters, and they're squared. All right, so pause there, get out your homework, get it done, and then come back when you're ready to check it out. All right, homework time. Number 1. Find the area of each shaded region. Show your reasoning. Okay, so I'm going to go ahead and I'm going to decompose this by drawing a line here, drawing a line here. I have a 2 by 1, 2, 3, 4, 5. So 2 times 5 is 10. Here I have a 2 times 1, 2, 3, 4. 2 times 4, which is 8. And a 2 times 2, which is 4. When I add those up, 10 plus 8 plus 4 gives me 22 square units for the A. For B, I recognize for me, what I see is I have a square and pieces missing. So I'm going to take the big square. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 times 6 is 36. And I'm going to subtract what I see on the inside. Inside here I have 4 and 4. So I can subtract the total of how much? 4 plus 4 is 8. So I'm going to subtract 8, and that's going to leave me with 28 square units. Alright, C. A little more complicated for C. I can decompose it first of all by drawing that line right there. So now I have this rectangle, which is 1, 2, 3, 4, 5, 6, 2 by 6, which means a rectangle has a value of 12 square units. But then I have that triangle on top, right? What we've done before is we've taken that triangle, we've decomposed it. We've cut it in half like that, and then I rearrange it by moving it over to here. It's a 3 by 2, so 1, 2, 3 by 2, and so it becomes that whole space right there. So the whole rectangle is a 3 by 2, which is going to be a value of 6. So 6 plus 12, 12 plus 6 is 18 square units. Alright, pretty cool. Alright, number 2. Find the area of each shaded region, show or explain your reasoning. So, there are different ways to do some of these, so here we go. This first one, I'm going to go ahead and decompose it by chopping it right there. I have a 2 by 2, 2 times 2 is 4, so that area right there is 4. This whole length is 6, this one is 6, but I already got rid of how much? I got rid of 2 right there, which really leaves this space right here equal to 4. So 4 times 6 is 24, so I combine 24 and 4 for a total of 28 centimeters squared. Over here we have the entire blue rectangle is 8 times 5 for an area of 40 centimeters squared, but I have this other part on the inside I have to get rid of. 2 times 3 is 6, so let's remove the white piece, 6 centimeters squared, so I'm left with 34 centimeters squared. For the letter C, same idea, except we have a bigger piece in the middle, don't we? Okay, so the blue part is going to be 15 times 10, or 150 centimeters squared, and I need to get rid of the white part here, so I'm going to subtract something. Well, 9 times 6 is 54, so I'm going to subtract 54 centimeters squared, subtract the inside part, and that leaves me with 96 centimeters squared for the blue shaded region. And finally, our last one, I would decompose this by cutting it right there, and then rotating that around to make that into a nice rectangular shape that has also a length of 8, so this 8 becomes that one there, that 5 becomes that one there, so I end up with an 8 times 5 rectangle, 8 times 5, which is going to be 40 centimeters squared for that shape right there. Number 3. It says 2 plots of land have very different shapes. I would say yes. Noah said that both plots of land have the same area. Do you agree with Noah? Explain your reason. So, Noah says they have the same area. This area matches that area. They definitely look different, but let's see if we can figure out what's happening here. What we notice with this one is a nice rectangle. The question is, can you turn this into that rectangle by decomposing and rearranging? I think the answer probably is, yep, you probably could. So if we were to first of all get a nice straight line to match that one over there, that's a pretty good deal. So far, if I just remove that, it's looking closer already, isn't it? Right? Where it just has a little piece, like a bite taken out of it. But what we notice about that shape right there, if I use some tracing paper here, back to my stamps, is if I take that shape and draw it, and then slide it over, what do you notice? Look at that. It fits right in that space. So, this triangle piece, if I decompose it and slide it over there to that space, actually fills that gap completely and perfectly. So if I take this piece and cut it again and move it over there, I have the same exact space. Then all I still have to do is decide, is this square, or rectangle, sorry, the same as that one? And when we slide it across, we would say, yes, it is. So do I agree with Noah? I definitely agree with Noah. Do I need to explain my reasoning? Yes, you need to explain your reasoning, so use your words and write down what you say. Alright, I talked you through it, now you write it down in your own words. Alright, and number 4. A homeowner is deciding on the size of tiles to use to fully tile a rectangular wall in her bathroom that is 80 inches by 40 inches. Alright, so she has a giant wall that's 80 by 40, whatever it's going to be, 80 by 40. The tiles are squares and come in 3 sides, 8 inches, 4 inches, 2 inches. State if you agree with each statement about the tiles and explain your reasoning. Okay. Regardless of the size she chooses, she will need the same number of tiles. Well, that doesn't make a lot of sense. Let's say I have a giant space to cover, right? If I have this giant space to cover, if I use the 8-inch tiles and some 2-inch tiles, those are very different sizes. I'm going to have a variety of sizes to make this work as it is, and realistically, I'm not going to buy the same number of everything. It just doesn't make a lot of sense. So it's not going to work for me. So we're going to say, no, I don't agree with that one there. That's a false one. Regardless of the size she chooses, the area of the wall that is being tiled is the same. So we're saying, no matter what she decides to put in here, whether it be big ones or little ones or a combination of stuff, does the wall size ever change? No. The wall size stays the same. That's true. She's not changing the wall, she's covering the wall. So that's a true statement. No matter what she puts on it, the wall stays exactly the same, the area stays the same. She will need 2 2-inch tiles to cover the same area as 1 4-inch tile. Alright, let's think this one through a little bit. Draw a picture. So let's say, here is a 4-inch tile. I'll make that 4. So it's 4, 4. Just drawing a sketch out. So if it's 4, that means if I cut it in half, that makes a 2 and a 2. If I cut this in half, that's a 2 and a 2. So how many 2-inch tiles are inside of 1 4-inch tile? 1, 2, 3, 4. So this says she'll need 2 2-inches to cover 1 4-inch. Is that true? No, that is false. She actually needs 4 2-inches, right? So 4 of the 2 inches, so 4 2-inches equals 1 4-inch. That's kind of hard to write. Let's do the next one. She'll need 4 4-inch tiles to cover the same as 1 8-inch tile. Well, let's just sketch that out real quick. So let's pretend this is an 8 and an 8, and we cut it in half. Cut it in half, so you have a 4-inch, 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 4-inch. How many 4-inch tiles cover the 8s? 1, 2, 3, 4. So that would be a true statement. Yep, 4 4-inch ones is the same as 1 8-inch. If she chooses an 8-inch tile, she will need a quarter as many tiles as she would with 2-inch tiles. Well, a quarter. A quarter is 1/4, right? So let's go back to our 8-inch tiles here, and let's just break it apart some more into 2 inches and see what we have. This was breaking into 4-inch tiles, so if I break the 4 into 2s, into 2s, into 2s, into 2s, how many 2-inch tiles are inside of an 8-inch tile? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, or 4 by 4, which is 16. So we can see that there are 16 2-inch tiles inside of there. So, is it going to be a quarter as many? Nope, it'll be 1/16 as many. That's how that works out there, not 1/4. So that would be a false statement for that one. So only B and D are true. Alright, that's it for today. Have a great one, and we'll see you next time.